All right, thank you all for joining us for the first high energy astrophysics lunch talk for spring 2021 in the era of COVID, all remote all the time. We have no pizza, but as you can see, we have digital backgrounds. Our first speaker for today is Javier Garcia, who received his bachelor's at Universidad de Zulia and a master's from the Venezuelan Institute for Scientific Research. In 2010, he got his PhD from Catholic University of America with Timothy Kallman and Stephen Kramer. He was a research associate at the University of Maryland before joining the CFA as a postdoctoral fellow in 2012. He then moved to Caltech and became a research assistant professor there. And he was a senior Alexander Humboldt Fellow in 2016 at Dr. Carl Reme's Observatory in Bamberg. He's a member of the New Star Science team and on various X-ray working groups, including Athena Links and XP. So with that, please do begin.
Thank you, Peter. Thank you, everyone, for joining. I'm very happy to talk to CFA people. I have a great time working there with Jeff McClintock and Jack Steiner. And pretty much everything I'm going to present today is a project that I started there during the time that I worked there, and we have continued through the years. So I'm listing probably the most important people right now in the project. I highlighted Riley Corners, who is my postdoc, who has taken the lead on this project in the last maybe 3 years. Jack, of course, and many other people have been contributing along with us. So I'll be talking about mostly X-ray reflection and spectroscopy, and this is a simple cartoon picture to explain what really that means. Maybe most of you are already familiar with it, but just in case, let me remind you what we think happens in the vicinities of an accreting black hole. And this also, by the way, could be applicable to neutron stars. So pretty much any compact object will tend to have an accretion disk. And
are you sharing your screen?
I am. I'm sorry. I thought I did. Let me try it again.
Okay, we can see your screen now. So now you just need your.
I'm sorry.
Your talk. There you go.
Yeah. Okay. So you see my list of collaborators there. Sorry about that. And this is the cartoon I was mentioning. So this picture is applicable, as I said, to almost any compact object that has an accretion disk around. And vast amount of X-rays are produced in the central regions. In this particular cartoon is depicted as a jet, which is one of the possibilities. But for the purposes of this talk and most of our fates and results, we talk about coronal emission because it could be just a hot plasma that produces tons of non-thermal X-rays, and they're typically seen as a power law in the X-ray band. And if those X-rays, a fraction of them, they will illuminate the disk, they will get reprocessed, and they produce a lot of fluorescence lines, and both emission and absorption features are produced. The typical one, the most important for reflection spectroscopy is these features here around 6 kV, 6 to 7 kV, which are due to iron inner shell. Iron is quite abundant metal, and it is in a region where there's not much else going on. So it's a line that is typically very bright in these sources. And you see this thing here is the Compton, is the iron KH in absorption. And then at higher energies, you see a bomb, it's referred as a Compton hump. It's produced by electron scattering in the disk atmosphere. But there is many other features in the spectrum. Now, if this reflection or reprocessing happens close enough to the compact object, then it will be affected by relativistic effects. So photons leaving the disk will be boosted or gravitational redshifted. And the overall effect is it tends to smear out the spectrum. And that's kind of the red line that you see, the red curve that you see where something like the green curve will severely be severely distorted and become like the red one. Which sometimes we see also some of the disemission in the X-ray band. So this is the general picture, and we use this technique for mainly, perhaps one of the most famous uses is to measure the black hole spin. And this is because the reflection spectrum is very sensitive to the location of the inner edge of the accretion disk. So the closer it is, the stronger the distortion we're going to see. And this can be mapped directly to the spin of the black hole. The fastest the black hole is spinning, sorry, the more it allows for the innermost circular orbit to approach closer to the object. So this is a very useful technique to measure black hole spin. However, there is a lot more that we can do. And that's what we've been working over the years to include more physics into the model, because precisely this dependency on the inner edge of the disk allow us to measure the degree of the truncation that sometimes has been claimed in accretion disk for, in the case of black hole binaries specifically. We can say things about the vertical extension. We can probe the state of the gas, what kind of, by looking at the atomic lines, we can say what kind of elements are present. And because reflection is also clearly dependent on what is the illumination geometry for the primary photons, we can then start saying things about the properties of that corona, which is somewhat mysterious. There's a lot of different ideas of what it can be, but we can start putting constraints in properties, general properties like temperature or the optical depth of whether it's extend or very compact. And lastly, it's being used to also probe extreme physics due to relativistic effects. And I'll talk about that towards the end of the talk. So going back to the question of the spins, I think in black hole binaries, there is a sort of renewed interest in looking at the distribution of the spins in this population of sources because of the new results coming out from gravitational wave detections and LIGO sources. And this is a somewhat out of date plot, but there is a clear, I can see a clear discrepancy or separation between the population of spins, the distribution of spins in black hole binaries measured in X-rays compared to those that are coming out from the gravitational wave detection. So that's at the very least interesting because it might point out to clear differences in the populations that we see. I also like to always remind that this technique is very simple to use, but that sometimes comes as a burden because it means that it depends of how careful the user is, what's the quality of the data. And this is a compilation right here of spin measurements for SIG-X1 over the years. And you can see, I said, this is not a real trend. This is just measurements over the years being reported and somewhat just changing. And it's funny to see that it looks like a trend, but what happens is we have, consistently we have better data and hopefully better models that are approaching towards a more concrete value. So this is a bit of a caveat. The project we've been running for a few years now, it started, as I said, at CFA under the leadership of Jeff McClintock. We wrote a proposal for NASA to study the 6 black holes. And what I'm showing here is the hardness ratio diagram for all of them. And what we're trying to tap into is the RXTE, the archival data for the RXTE satellite, which is not operational anymore, but has provided almost daily observations for many, many black holes. These are just 6 very bright, very, very interesting sources that we picked for this proposal. And the aim is to try to apply reflection spectroscopy as much as possible and learn the most that we can from this. So this started with GX339-4, which is normally referred as a prototypical black hole because It does almost everything that you can think a black hole binary should do. It produces regular hours every 2 or 3 years. It was observed about maybe 5 or 6 hours during the lifetime of RXTE. So there's plenty of data, as I'm showing here in the plot. And we started concentrating in the Hatter state, and the boxes right there define regions in which we decided to combine data just to get the most signal possible. And the reason is because RXTE was a great instrument with great sensitivity, but it has a poor spectral resolution. So 1 kV at 6 kV. So we wanted to get, there's nothing we can do about resolution, but we can try to maximize the signal that we get. So when you look at the spectra in those 6 boxes that we define, and you make a ratio plot to a power law model, you immediately see very clear signatures of reflection. This is that iron line being relativistically broadened, the iron KH, and signatures of the Compton hump. And it's also very obvious that they're not identical. When you move, this is in the vertical axis, you're moving up in luminosity. The source is growing in luminosity as it starts and outbursts. So clearly things are changing. And we fitted this data with the model called RELXILL, which is a model we have developed in collaboration with several people in Bamberg in Germany. And it includes, it gives you the possibility to fit for both the non-relativistic and the relativistic reflection, which are typically required. And you can see, without going too much into the details, it does a great job in fitting this data, which contain a lot of signal. The 6 combined spectra are about 77 million counts in the X-ray band. So we were able to measure the spin to a high value, which is consistent with most recent determination, the inclination of the inner accretion disk and the iron abundance. But perhaps the most interesting aspect at least for me, was the fact that we were able to look at evolutions of parameters. So this is a plot of how the inner radius seems to be moving inwards as the luminosity grew and in the outbursts, right? So this is going in the vertical direction in the Q diagram that I showed before. So it looks like the inner radius, as seen from the point of view of reflection, is moving towards getting closer to the black hole. And this yellow line here is a high energy cutoff of the spectrum, which we relate to the temperature of that corona that produces the power law emission. So this shows that as this moves inwards, the corona is getting more, is cooling down. The temperature is going down, and that is consistent with a Comptonizing plasma that gets more luminous. Ergo, the photons leaving the plasma will carry energy and will tend to cool it down. I find it interesting that this sort of happens in a nice choreography, because this is moving inwards, the corona is getting cooler, but yet the slope of the power law remains about the same in that vertical branch in the Hatter state. So there is no physical reason for this to happen, and I still don't quite understand why that is. Why to maintain that slope? I find it interesting. Regarding the location of the inner accretion disk, it turned out to be a bit of a mess, because we compare our results, which are shown in red here, with several other determinations in the literature. This is all for this same source, for GX339-4. And it's a bit of a mess of a plot, but the important thing to distinguish here is there are clearly 2 different tracks. This is luminosity in the horizontal axis versus the inner radius in the vertical axis. And you can see that there is a group of determinations for the same range of luminosities that predict a much larger truncation, about almost 2 orders of magnitude larger. Now, the bottom branch, which is where our results are, contains points from taking measurements taken with many different instruments, Suzaku, RXTE. Much recently, we have follow up with SWIFT, XRT, and NuSTAR. While the blue points on the top branch are all, the common characteristic is that they're all taken with XMM Newton in a particular mode, in timing mode. which I believe they might have some problems with the calibration. It's also very prone to pile-up effects that will tend to alter the shape of the spectrum. So that is the one thing that I found that could explain why the results are so discrepant. However, to make things more complicated, because nothing is easy ever, there are results derived from timing analysis that tend to agree more with this branch than the bottom branch. So this has created a lot of debate among the people, among the community that look at this issue. We look at both GX339 and this other source H1743, and by just measuring the inner radius through reflection spectroscopy, you see there is a common trend of again with luminosity. The higher the luminosity, the closer the inner edge, the smaller the inner radius is. And a similar trend was reported by timing analysis by looking at the reverberation lags. And if you translate the reverberation lags to a distance, you can then put a distance to what you think the inner radius might be. And if you do that again, the trend is very similar. They're almost identical, but they're off by a large margin. And this might be just based on a very simplistic interpretation of the timing signature of those time lags. It requires a proper physical model to explain. So it might be we're just simply measuring the same thing, but with different units. But this hasn't been necessarily clear out yet. So if I redo this plot, we have, as I mentioned before, we have follow-up with modern instruments like NuSTAR, which is also impervious to pile-up effects. And recent hours following up the same source every time it goes into hours is still consistent with a relatively low truncation in the higher state, still within that low branch. So if I, for PR purposes, if I remove or ignore all that upper branch, the plot looks a lot nicer in the sense that we still preserve this nice trend going from low luminosity to high luminosity, and the inner radius moving inwards. Recently, student Navin Esridar, he worked on looking at the transition for the same source for GX339, transition between the high and the soft state. And he derived estimates for the inner radius from fitting the continuum, the thermal emission of the source of the disk, and making simple assumptions or reasonable assumptions for the mass and distance. You can derive an inner radius, and then he compared that to derivations from reflection spectroscopy for that same, going in the horizontal branch in the Q diagram. And there is a remarkable consistency between the results. So that tells us that probably by the time the source starts to transition to the soft state, the inner radius must be already close to the ISCO, to the inner most stable circular orbit. So we continue this work. In the case of J1752, Jack Steiner pointed out back in the day that there was this remarkable aspect. This source sat on the higher state for about a month without changing much luminosity nor spectral slope. And that we took that data, it comprises about a month of exposure if you take all together, and it came out with a single spectrum with 100 million counts in the 3 to 45 kV band, plus a few more million counts in the XTE band, so extending all the way to 140 kV. So this was a remarkable spectrum. With push the models to the limit. We have to revise pretty much all the models at the time. And I don't have time to go through all the details. We fitted different models, different versions of the same reflection models, considering different aspects. And in particular, we look at the geometrical configuration for the illumination. You can either choose the illumination to follow some power law for the emissivity of the disk, or assume a lamppost where you have a point source sitting in the axis. And the results are all consistent except for the inclination. The inclination came out to be very different. with the lamppost geometry being more consistent with determinations from the radio jet. So this already is poking into telling us that we can use these techniques to say good things about concrete things about the geometry of the illumination. In this case, the inner radius also turned out to be very close to the ISCO. There's a recent paper by Sidiarsky et al. That have reanalyzed the very same data that we published, and they argue that this is actually truncated about 100 Gs again. The argument here is they claim that the coronal plasma, that corona that produces the power law, it shouldn't be homogeneous, shouldn't be a single temperature, should be a multi-temperature plasma, and therefore it shouldn't explain the broadband spectrum, or you shouldn't be able to explain it with a single temperature as we did. However, they only fit the 4 to 10 kV region and leave everything else out. So I'm not quite sure how to interpret these results, but I figure I just mentioned because I thought it was interesting. Recently, Riley Connors has done a lot of work on continuing looking at all the other sources. In the case of J1750, this is an interesting source because it has very good determinations of spin with an alternative method, the continuum fitting method. So that means that we can fix the spin and pay attention to other parameters. We look at one particular set of observations in a very bright state, in the intermediate state, getting close to the soft state, and we were able to fit very well this very broadband spectrum from 1 to over 100 kV. Once again, with reflection models, they have thermal emission. It looks like it is also a component of very high energy that might be coming from the jet. The interesting aspect of this work is that no matter what we did, we couldn't recover the orbital inclination for the system, which is also very well measured. It's measured at 75 degrees, so it's a high inclination source. But reflection, no matter what you do, wants it to be at 40 degrees. So once again, we're tapping into understanding more about the geometry of the system. Could it be that there's this misalignment? Could it be there's a particular geometry? I propose, this haven't been tested yet, but I propose that one possibility is because the orbit is so inclined, there is some obscuration by the disk itself of the central region. And there are simulations of reflection models that show that if some obscuration like this occurs, you will tend to see an iron line that looks more like a low inclination line, what a low inclination this will produce. So this is an artificial aspect of the model. So we're still kind of investigating this. It will be actually very interesting if that's the case. And much more recently, on the same source on J1550, when we look in the soft state, we found serendipitously a signature that we interpret as returning radiation. These are photons that are emitted in the disk that go, their path are curved so much by the relativistic effects that they illuminate the disk back again. So this happened because there was a strong requirement for the data to have a reflection spectrum that had no Compton hump at all. And the only way to fit this data reasonably well was to use models that were actually developed for neutron stars, where instead of a power law as illumination, you use a black body illumination spectrum. And this turned out to work very well to fit the data. So we interpreted this as a signature of it's reflection, but reflection from radiation that has been returned to the disk. So thermal radiation that came back to the disk and then got reprocessed. We recently also looked at 4U1630, where we confirmed that this sort of model actually works well in this case too. So whenever you have a very bright soft state with a strong thermal emission, it seems like the data tends to prefer this sort of interpretation. This paper was just accepted, so it's in the archive if anybody wants to see it. And once again, we look at this comparison of deriving inner radius from the thermal emission, because it's so prominent in this source, with respect and comparing it with those from doing the reflection constraints. And as before, they're very similar. They're not in perfect agreement, but they're at least in same sort of order of magnitude, below 10 ISCO rather than 100 times what has been proposed in these other sources. So I'll finish here. I'll say that what we have learned is, first of all, that this RXTE archive, which seems so limited in spectral resolution, it has this tremendous potential to give us a full view, a panoramic view of what's the behavior of these black holes. But to my surprise, it has also, because the data is so significant, the statistics are so good, it have given us a lot more than they have given us an insight into the details of the physics in these sources. And for sure, X-ray reflection spectroscopy, I hope you're convinced that is an extremely powerful tool to do these sort of things. And I'd like to finish with remembering our dear friend and mentor, Jeff McClintock, who was, again, the leader of the starting of this project. And I shared this is literally the last email, the last line of the last email that we got from him. He was always so passionate and so enthusiastic about this. And my only hope is that we actually keeping up with the work as he wanted. So thank you, and I'll happy to take questions.
Thank you, Javier. We have time for a couple of questions. If you raise your hand in the participants window, we can call on you, or if you'd rather have us read it from the chat, we can do that as well.
Hello?
Yes.
Yes, so could you go back to your slide on GXPT 9-4 in the beginning when you were showing the luminosities of the inner radius?
Yes. Maybe this one or the one before?
One before that. So that
This one?
Nope, even earlier than that.
Maybe this one?
Yeah, this one. And so if I look at the first 2 points and the last 2 points, they seem to be within a sigma of each other. I mean,
You're talking about the first 2 points right here, these ones?
mm-hmm.
Yeah, so
with the straight line.
yeah, so these are this is because those are the lower luminosity regions where the signal is not as good as in the brighter ones, right? So your determination for the inner radius is certainly not the greatest. Yeah.
I understand that, but because you don't have very accurate measurements at the first 2 points, it seems to me that it's not really a very large trend.
Yes, I will agree with that. But perhaps I definitely wouldn't fight too much about whether these inner radius are 4 or 5 or 6. I think the interesting question is whether you are here or all the way up here, whether it's of the order of tens RGs or of the orders of hundreds, right? So I think that's an interesting question, and I think those constraints, albeit not great, they do rule out extreme large truncation.
Yeah, that's fine. Thank you.
Okay, we have one last question from Laura Brenneman. Javier, great talk. Has anyone looked at AGN in the RXTE archive to see if there are enough counts per source to do similar work?
Good question. The quick answer is I'm not sure. There was a big project in San Diego, in UC San Diego. I think it was run by Rick Rothschild, where they had this whole catalog of AGN loop with RXTE. And I think they were trying to derive simple fits with perhaps even including reflection. But I don't know much more about that. Maybe AGNs were not so targeted as black hole binaries by RXTE, but that will be a place where I will look into for sure. I can find it if you send me an email. I can go and find it.
All right. Thank you again, Javier. We have a sign-up sheet if you want to meet with him via separate Zoom meetings, linked from the email notifications. And now we can move on to our next speaker.
Hi, everyone. Our next speaker is Shifu Zhu. He's a fifth-year graduate student of astronomy and astrophysics at Pennsylvania State University. Before that, he attended the University of Science and Technology of China, where he finished his Bachelor's of Science in Astronomy in 2013 and received his Master's in Astrophysics in 2016. Shifu's work on quasar jets was the topic of a Chandra press release back in last October, for which he also wrote a piece for the Chandra blog. So without further ado, Shifu Zhu.
Thanks. Could you see the slides?
Yes.
Okay. Hi, everyone. Today, I'm going to talk about a project we have done in last year. We studied the correlations between the primary continuum that is radiated from the corona, the disk, and the jet of radio loud quasars. And I want to start from the spectral energy distribution of quasars. There's two types of quasars that they have quite different radio properties. One of them being the radio loud quasars, and another one being the radio quiet quasars. They have quite similar optical UV properties. However, these radio loud quasars have very strong radio relativistic jets that making them very luminous in the radio band. And these jets is generally being absent in these radio quiet quasars. And there is some notable differences in their X-ray bands that I will focus on today. First of all, the X-ray emission of radio quiet quasars radiated from the so-called disk corona. And this X-ray emission correlated with that UV radiation radiated from the disk, and which is not unexpected given that this X-ray emission was mostly radiated by the inverse Compton scatter process, that is the seed photons of other thermal radiations from the disk. And as to radio loud quasars, and the first thing we know is that their nuclear X-ray emission is more luminous than that of radio quiet quasars. Like this line, this black line represents their LX-LUV correlation for radio quiet quasars, and this blue and the red dots are radio loud quasars, and they generally lies above this black line, meaning that there is extra X-ray emission from radio loud quasars. And if we divide their nuclear X-ray emission by their X-ray luminosity expected from radio quiet quasars, we get the amount of excess X-rays. And this excess X-rays depends on the properties of the jets. The R represents the so-called radio loudness parameter, and this the second dependence is on the radio luminosities. And another thing we know is that this here is a image of a X-ray image of a radio loud quasar. It tells us that this radio jets are not only luminous in the radio band, they could also be luminous X-ray sources. So people speculated that this excess X-rays are radiated from the base of the jet. And here is a sketch explaining how these models, what these models represent. It suggests that in the radio loud quasars, there is a corona that is similar to that of radio quiet quasars, but there's more X-rays radiating from the base of the jet when this jet getting more powerful, more X-rays are produced and produce the correlations we have seen in previous slides. And last year we did a project and investigated this further, and we found that this might not be the case. And we see our sample are selected from the SDSS, and these radiological quasars are all optically selected. And we matched these optically selected quasars with Chandra and XM Newton archives that produce our list of radiological quasars with X-ray coverage. And most of the X-ray coverage is serendipitous, meaning that we get a largely unbiased subset of the parent sample, and we further match the list with the first and the NVSS catalog to calculate their radio band luminosity, and we also measured their radio band slope. And it turns out this radio band slope is very important. And the radio emission from a radiological quasar could come from the lobe, the jet, and the core region. And the radio emission from the core region usually have a flat spectrum, but the radio emission from the lobe and the jet is usually steep. And in this sense, radiological quasars can be divided into two types according to their radio slope, one of them being steep spectrum radio quasars, and they are usually lobe dominated. Another type is flat spectrum radio quasars, and their radio slope being flat could be because we are observing these quasars down along their jet, so their radio emission is beamed. Another reason is that these objects could be intrinsically lacks this large scale radio emission, so we only see their radio core, and this is not related to their viewing angle. And we further cleaning our sample by their colors and also SDSS spectrum to making sure that the resulting sample is typical and they have a blue continuum in their optical UV. And we are looking at their primary continuum from the disk and the corona without extinction or absorption by intervening material. And the first thing we did is to study their LXL UV correlations and compared that with radioquiet quasars. We divided our samples according to their radio slope into flat spectrum radio quasar and steep spectrum radio quasars. We can now focus on these steep spectrum radio quasars. The first thing we noticed is that this steep spectrum radio quasar have a LXL UV correlation that is consistent with the RQQs in slope. It's just their normalization or the intercept of this line is shifted upwards. And things got more interesting if we divide our sample into beams of radio loudness. We divide this steep spectrum radio quasar into 3 different radio loudness beams and study their LXL UV correlation separately. And they always have a consistent relation with that of RQQs. And if we put this result into the context of their previous interpretation about the nature of nuclear X-ray emission of radiological quasars, their total X-ray luminosities follows a correlation with the UV luminosity with a slope of 0.6. And there's a coronal component that also follows this correlation, which we learned from radioquiet quasars. And an unavoidable result is that the jet X-ray emission must also follow this correlation. And this is result is in contrast with the definition of a jet component, because by definition, this jet component it should not correlate directly with the emission from the disk. So a more natural explanation is that for these steep spectrum radio quasars, we do not need a distinct jet component. All these X-rays could come from the corona, and it's the normalization factor that depends on the radio loudness, and this correlation indicates a corona jet connection. So this slide shows a sketch of our new explanation in contrast with the previous picture. The X-rays, the nuclear X-rays of radio loud quasars are dominated by the corona, and the brightness of the corona increase with the radio loudness parameters of the radio loud quasar. As to flat spectrum radio quasars, the correlation analysis shown in previous slides cannot give a very clear, cannot reach a clear conclusion. However, we can still gain some insights by comparing their X-ray, their excess X-rays of flat spectrum radio quasars with these steep spectrum radio quasars at a fixed UV luminosity and the radio loudness. Here, the large symbols represent the median values of their excess X-rays in 3 radio loudness beams. We can see that their median values of these 2 types of radio loud quasars are very similar. They differ only at the level of 10 to 20%, meaning that there might be a jet-linked component in flat spectrum radio quasars. However, they could not dominate their overall X-ray emissions, and they are probably only important in a small fractions of these flat spectrum radio quasars. And we can look further into these corona jet connections in steep spectrum radio quasars. Here, we compared these steep spectrum radio quasars with a small sample of radio quasars. These are PG quasars. They have very deep radio data and allow us to constrain their radio loudness. And this plot showing the dependence of excess X-rays on radio loudness across a very broad range of radio loudness parameter. Since the values for this radio quiet quasars are scattered around 1 for this radio loud quasars, they increase with the radio loud parameter, and this dashed line for the radio quiet quasar and the solid line for the radio loud quasar are obtained independently. They match with each other, like quite surprisingly, as their value of around the radio loudness parameter, as the value of radio loudness parameter around 10, which is the usually dividing line that we separate these radio quiet and radio loud quasars. So there must be a break as the radio loudness parameters about 10. And this plot supporting the idea that radio loud quasar and the radio quiet quasars are intrinsically different objects. And they might have very different accretion flows. In these slides, we study the overall LX, LUV, Lradio correlation for steep spectrum radio quasars. And in the plot at the left-hand side, we divide the sample we studied their LX versus R correlation, but divided into beams of UV luminosity. At the right-hand side, we studied their LX, LUV correlation divided by radio loudness beams. In both plots, there is always one of the correlations that controls their slope, and another quantities that controls their intercept of these correlations. So there must be two statistically independent relations at work, and one of them being their disk-corona coupling, which works for both radio loud quasar and radio quiet quasars. But there's another corona jet connection that is at work only for radio loud quasars. And we can call this quantity that we have very often used in previous slides a X-ray loudness parameter. And we show our sample into the plane of Lradio versus LUV. And also we have some data points for radio quiet quasars. And we color coded their data points with their X-ray loudness. In this direction, this is the increasing direction of radio loudness. However, according to the color of these data points, this is also the direction of increasing X-ray loudness. So this is another way to express our corona jet connection. In the literature, there's a so-called disk jet connection, which is the correlation between the radio luminosity of the jet and the disk the UV luminosity from the disk. And this correlation is in orthogonal direction with the corona jet connection we discussed. So the point is that this corona jet connection is not a side effect of the so-called disk jet connection. So overall, the radio loud quasars could feature a disk corona coupling, a disk jet connection, and also a corona jet connection. There must be at least 3 independent physical processes that are controlling these correlations. And in summary, our result showing that the quasar jets contribute much less to the nuclear X-ray of radio loud quasars than we previously thought. And there's a corona jet connection. And this corona jet connection implies that the small scale process.
Shifu, I believe you're muted. Unless that's just me.
I can hear him.
Can you hear me?
I can hear him.
Okay.
Yeah, you're fine.
And so, I think that's it. It's a small scale process, and this might be the magnetic field that controls both the launching of the jets and also the brightness of the corona. And I will stop here. Thanks.
Thank you, Shifu, for a wonderful talk. Sorry for the interruption at the end. I think that was my speakers acting up. If there are any questions, please feel free to put them in the chat or raise your hand or just speak up, I guess, because there aren't very many raised hands or anything in the chat. I'm hearing someone trying to speak, perhaps.
I can ask a question. In the SDSS sample, do you have many radio measurements for objects that are radio quiet?
No, we have a cut for the read loudness parameter, and we only keep the read loud samples.
It would be, but there is, as you pointed out, for the PG quasars, there is radio emission for the radio quiets. If maybe it's not sensitive enough with the Sloan sample. I wonder how much more sensitive than VLASS you'd have to be to start picking them up.
I think now it's the first catalog is not deep enough to have a very strong constraints on the radio loudness parameter for radio quiet quasars. The VLSS will certainly improve that. But since we only have the first epoch data and the dips of the single epoch data of VLAS is comparable to that of first. And I don't think for now, at least, it's not easy to have a complete, have a good radio quiet sample with a complete, very good radio constraints. But maybe in the deep fields that can be done. Is that your question?
Yep, I guess so. We probably have to wait for SKA or something to do that.
Yeah, yeah.
All right. Any other questions? Belinda, yes, please go ahead. Oh, your mic is not working. Okay, if you put the question in the chat, I can ask it for you. So we're, okay, thank you. So Belinda Wilkes asks, as well as the radio loud quasars being brighter, they also show flatter X-ray spectral slopes. Can you explain this in your model?
Yes, actually we are performing a project that to study the X-ray spectrals. And our answer is that in the previous studies, indeed, that the radio loud quasars always show a flat X-ray spectrum than radio quiet quasars. I think it's about how you select your sample. In the radio selected quasar sample, you always have a significant portion that is a beamed object. But when you study the optically selected sample, the beamed object is only a small portion, and the overall X-ray spectral slope is consistent with that of radio quiet quasars.
All right, thank you. Any last questions? I don't see any more. Well, if you would like to talk to Shifu, his schedule for meetings is still open for today and tomorrow. So please go ahead and sign up. And well, before we end, I would like to say one last, there's one last announcement. So Peter and I are very happy to have Federico Fraschetti join us on the organizing committee. So now if you have any comments or suggestions or thoughts about the seminar, you can contact all three of us. So again, thank you everybody for joining us for our first high energy seminar of the semester, and hope to see you at all of our future ones.